Okay, hope you're doing well out there. We're going to cover this problem, which is based on what's called a heating curve, although it's not really curved, it's more like a heating graph. Nonetheless, it shows the temperature on the y-axis versus the amount of heat added to a substance, and this is going to be water in this case, and we're starting off with ice at negative 20 degrees. So if you plotted this kind of on the graph, we'd start off with the ice here. As we add heat, we're going to have an increase in the temperature until we get to the melting point. So essentially, at this, for water, that would be 0 degrees. And then we're going to have a phase change. So then we're going to have a horizontal line. And I can just kind of mark this here with solid. This would be melting, or what we call fusion. And then again, that's going to be solid to liquid, the melting phase change. Once we've melted all the ice, it'll now be liquid at 0 degrees Celsius. And then we'll heat up the liquid, or we'll add heat to the liquid, changing the temperature of it, warming it up to the boiling point, which would be 100 degrees Celsius. So at that point, we have another phase change, and that'll be green. And that'll be a vaporization phase change, liquid to gas. Oh, by the way, this is just the pure liquid phase, this red line. Once we've vaporized it completely, we'll have gas at 100 degrees, and then we can finally raise the temperature up to 150. That'll be our final temperature of the gas. So what we have here is a way of looking at, again, the temperature of this substance undergoing this added heat. And we have two kinds of processes. So we have temperature change processes, which, if we could break it down, would be like basically steps 1, 3, and 5. And then we have phase changes, which would be steps 2 and 4. So when you add heat, or if you remove heat from a substance, you can either change the temperature or change the phase, but never do both at the same time. That's kind of the bottom line. And this is a very long problem. It's actually a book problem from chapter 10. So we'll go through each part. It's long because we have to do the calculation for basically all these quantities: Q, W, delta E, delta H. But this is the one that I always mention as, if you're going to do one kind of review problem, this would be the one to do. Although don't do just one review problem, do more. But this is very comprehensive, and it's also got some chapter 9 concepts, so it's good as well. Going back during the final kind of review process, this is a good one to kind of look at and just go over again. It'll be good to kind of brush up on all these things. So we'll start with Q, and for Q, we're going to use either NC delta T or MC delta T, depending on the units. That would be your equation or equations for temperature changes. And phase changes, we're just going to basically use the enthalpy of that and multiply by the moles. So we'll see, like for Q, in this total process, it's going to be Q1 plus Q2 plus Q3 for each step. So step 1 will be temperature change. And then step 2 would be phase change, and then temperature change, phase change, then temperature change. So step 1 will be N times the C of ice delta T. And then step 2 will be N delta H fusion. Step 3 will be N, this heat capacity of liquid delta T. 4 would be N delta H vaporization. And then 5 would be NC of gas delta T. Just make sure you use the heat capacities for the respective substances in each of those temperature changes. I should mention, by the way, these heat capacities are per mole. That's why I'm using N. If we were given the specific heat capacities, obviously that would be per gram, and then we use M. So we're just basing this on the units that are given, and now we can plug things in. One thing you'll notice too is that the enthalpies are in kilojoules, right? And the heat capacities are generally in joules. So you want to keep this in mind when you start plugging in these numbers. So this would be, we have 2 moles of water or ice, and then this is 37.5 joules per Kelvin per mole. This initial temperature will be a 20-degree change because we're going from -20 to 0. And then we have 2 moles. The enthalpy of fusion is given in kilojoules per mole, so I'm just going to turn it into joules, right? And there's that different number multiplied by 1,000. And then we have, this is 2 moles, we'll just leave out the units, and the heat capacity of liquid is 75.3. This is going to be a 100-degree change. And then we're going to have step 4, which would be 2 moles times the enthalpy of vaporization. Again, just multiplying that number by 1,000, so it's in joules instead of kilojoules. And then we have, lastly, 2 moles. Heat capacity of ice is 36.4 joules per mole per Kelvin, and that's a 50-degree change. All right, so each of these changes in temperature, we did final minus initial for those. And then, so basically Q total, adding all this up, is 113,600. So let's make it 114 kilojoules. Okay. All right, got 1 quantity. We only need to do 4 more. Luckily, some of these aren't as tedious. So with work, for example, remember there's only work if there's a volume change, right? There's no work if there's no volume change. So when we kind of break this down in terms of the different steps of this process, when we're heating up the amount, the sample of ice, it's not really changing volume. Even melting the ice to liquid, not really much of a volume change. Heating up the liquid, same, not much of a volume change. So steps 1, 2, 3, we're assuming because the volume change is so small, this work is going to be negligible. So assume no volume change. Okay, now we get to step 4. We're vaporizing liquid to gas. That's going to be a big volume change. And then step 5, heating up the gas at constant pressure. Imagine heating up a balloon. That's going to expand. There will be a volume change for that step as well. So for steps 4 and 5, there will be work, right? So we have work for these 2 steps. Also, you can predict that it would be negative because you're going to be expanding in both those steps. Might be also good to review those concepts about predicting the volume change in work. So let's figure this out. So work 4, we can do this, or if we think about what's happening in step 4, we're basically taking 2 moles of liquid, turning it into 2 moles of water vapor. So if you recall, we can also use this equation based on the ideal gas law, negative delta N gas RT, and the change in the moles of gas would be 2 moles of gas minus 0 because we have liquid, so we have a plus 2 mole change, right? So this would be a much easier way to figure out the work is just find the moles of gas. Since it's a phase change from liquid to gas, we can look at the process and then easily figure that out. And then we can plug in R, or constant, and T, this is 100 degrees Celsius, right? So this is happening at that temperature, 373 Kelvin. And this work is, it's negative 6.2 kilojoules, right? We're expanding, making gas, doing work. And step 5, again, we can look at what's happening. So the step 5, heating up the gas. Now we're not changing the moles of gas. In this step, we're just changing the temperature of the gas. So this would be a good example where we can use, instead of this, negative nR delta T, right? Because now we're just heating up the gas, basically 2 moles of gas from 100 degrees Celsius to 2 moles of gas to 150, right? So there's no phase change, just a temperature change. So we go 2 moles, R, joules per mole Kelvin, and then we go 50-degree change, right? And then that's going to give us this number, which would be about negative 0.83 kilojoules. Okay, so the work total is just the steps 4 and 5, which is basically about 7 kilojoules. If we add those two together. -7, it's doing work, it's expanding. Okay, so like I said, good review of some chapter 9 concepts. And now for the next two, it's not that bad because we can, if we think about it, we don't have to do delta E for each step. We can just find the delta E for the whole thing by adding up the total Q and W, which ends up being 107 kilojoules when we add those together, right? And then also for delta H, we don't have to do this for each step because this whole thing is constant pressure. So what is delta H equal to if it's constant pressure? It's equal to Q, right? So constant pressure, this is always true. And we have that number already, 114. Okay. So not too bad. And now we get to entropy. Entropy is also going to be one where we have to do each step. It's kind of like Q and W. We're going to have to break it down. So for entropy change, if you recall from the last video, going back here, there's kind of two equations depending on, in this case, depending on what's happening. Temperature changes, we're going to use the entropy change that looks like this, right? NC ln T2 over T1. And phase changes, we're going to use like similar to, should make this color coded, similar to heat. This is going to be N delta H, except we're going to divide it by T. If you remember, delta S is like Q reversible over T. That's essentially where this comes from. So we have, for temperature changes, you know, an equation for Q, an equation for delta S, and same thing for phase changes. And it's going to be very similar where we just kind of go back and forth. We have first a temperature change, so it's going to be NC of ice, ln T2 over T1. Then it's going to be fusion, so we do the N delta H fusion over the temperature. And it's going to be NC of liquid, ln T2 over T1. And it's going to be the vaporization, so N delta H vape over T. And lastly, NC of gas, ln T2 T1. And now again, we just plug things in and watch the units. So we have 2 moles, we have 37.5 ln. Here we gotta be careful, we have to use Kelvin, so it's gonna be 273 over 253. Definitely can't use Celsius when we have these absolute temperatures. So then again, I'm gonna put this into joules. So it's gonna be 2 times that, joules per mole, over the temperature again in Kelvin. And then we have our liquid changing temperature. That process would be that one with the 2 temperatures. The vaporization would look like this. This would be 373 for the vaporization temperature. And then lastly, heating up the gas, we have 2 times 36.4 times ln of 423 over 373. Okay. So that all should sum up to 324. This is going to be joules per Kelvin. Remember, entropy is kind of energy over temperature. All of these are positive, by the way, which you should be able to predict like we did in the previous video. Increasing entropy if you're heating it, increasing entropy if you're going from solid to liquid and liquid to gas. And this would be the total entropy change. All right, well, there you have it. And like I said, good one to work through on your own. Make a note for this one to come back to and review when you're doing maybe your last comprehensive final review. It kind of hits a lot of bases and covers a lot of concepts. All right, talk to you later.